In this series, we would be discussing the solutions to problems given in the following book. So this is a book on quantum optics by Professor Mark Fox. He is a professor at University of Sheffield. So this is an introductory book on quantum optics, and it covers a wide range of topics, and it is a good book for senior undergraduate or masters or entry level graduate students to basically study and get familiarized with concepts in optics and quantum mechanics and photon statistics, and basically the topics in the field of quantum optics. So we would be looking at the solutions to the problems given at the end of each chapter in this book. To start off with, we would start with chapter 2. Now essentially, the first chapter of this book is just how to read this book. So, and some introduction, some history on quantum optics. So the first chapter essentially turns out to be chapter number 2. The first chapter with some problems given in it. So this is chapter 2 on classical optics. Chapter 2 on classical optics. So we would start with classical optics and slowly build our way towards quantum mechanics and quantum topics. So let us look at the first question given in this book. So the first question is exercise 2.1. So this question says a plane electromagnetic wave with a constant amplitude E and wave vector k propagating through an isotropic dielectric medium with relative permittivity of epsilon r may be written in the following form. The next part is, the first part of it is show. There are two parts to this question. The first part says show that the wave is transverse provided that epsilon r not equal to 0. The next part says discuss what might happen when epsilon r equal to 0. So let us start solving this question. So from Maxwell's equations, so one of the Maxwell's equations is the following. So this is the divergence of the electric displacement vector is equal to the free charge density. Now this in this question we have the free charge density equal to 0. There is no free charge placed in this medium that we are considering. So for our case, when the free charge density is 0, we would have the divergence of the electric displacement vector to be equal to 0, and the electric displacement vector is given as follows. So let us just put this electric displacement vector in this Maxwell equation. So we get divergence of electric displacement vector is equal to the following. So let us now solve this. So epsilon naught is a constant. We can take it out. Then from the properties of divergence, we will get the following. This is from the properties of divergence, where we do not consider epsilon r to be a constant. So we have the following property of divergence. If we have del dot something like this, then this turns out to be so for the case when this small a is a constant, this term would go to 0 and we would simply get this. But when this small a is not a constant, then we would have the gradient of it also involved in this expression. So let us further expand this. Now this term over here for our case would be 0. Why? Because we have an isotropic medium. Sorry, I wrote the spelling over here wrong. This is an isotropic dielectric medium. So we have an isotropic dielectric medium. So for isotropic, it means that the relative permittivity epsilon r does not change with direction, so it is same throughout the medium. So for isotropic case, this epsilon r is a constant, and hence the gradient of epsilon r would be 0. So we are simply left with the following term. So this E naught can be written in component form. So we are just writing it in component form. And similarly, we are expanding K dot R. We have simply written these vectors in component form. So this is K vector, and then for E naught, now let us simplify it. So we will apply the divergence to each of these terms. So this whole thing that is there, so we will apply the divergence. Applying the divergence, we will simply get the following. Oh sorry, I seem to have forgotten omega t over here. We will have omega t as well. Also r vector is nothing but xi cap plus y j cap plus z k cap. This is the r vector. So this is coming just from the standard definition of divergence that we have, the above step. In this step we just used the divergence, applying the divergence to this exponential. So divergence of this whole term over here, e naught, so divergence of e naught x e to the power I kx x would just be e naught x I kx, sorry, the divergence of this whole thing, we have e naught x I cap e to the power I kx x plus ky y plus kz z minus omega t plus e naught y j cap this exponential plus e naught z k cap this exponential, and then taking the divergence we would get this step. And then this term over here kxx plus kyy plus kzz is nothing but k dot r. We had just expanded that over here. So finally what do we get? We get so this term in the square brackets over here, right here, is nothing but I, the imaginary number I times k dot e. So you can see this is kxx times e naught x e to the power I k dot r minus omega t. This is kyy e naught y e to the power I k dot r minus omega t. Kz e naught z e to the power I k dot r minus omega t. So this is nothing but k dot e vector times the I. This is because our original e vector was given like this, e naught e to the power I k dot r minus omega t, and e naught we had written in component form like this. So this is what we get. Now from the Maxwell's equation, del dot d is equal to 0. We have written it over here. So this thing is equal to 0, which implies epsilon naught epsilon r I k dot e is equal to 0. Now all of these terms are constants, so these are not equal to 0. So this implies k dot e is equal to 0. Now when our two vectors, when the dot product of two vectors is 0, that means the two vectors are orthogonal or transverse. So if k dot e is 0, this implies that k and e are orthogonal or perpendicular or transverse. So if k and e are orthogonal, so this means that the wave given by this electric field is transverse. So the transverse, for transverse wave definition is that the direction of propagation is perpendicular to the field amplitudes or orthogonal to the field amplitudes. So we have solved this question. We have seen that k and e are orthogonal, meaning that the wave is transverse. So the second part says what happens if epsilon r equal to 0. So in this case, there is possibility that we can get longitudinal waves. So the waves may not be need not be transverse. So if epsilon r is equal to 0, then we would get longitudinal waves and not transverse waves. For non-zero epsilon r, we saw that we are getting transverse waves, but for 0 epsilon r, the waves can be longitudinal. So this solves our question. I've looked at the first question of this book, Quantum Optics, An Introduction by Professor Mark Fox. I would be providing the link to Professor Mark Fox, to the website of Professor Mark Fox. You could visit his website. He has written certain other books also, and you could check them out from his website, the courses and the teaching work and the books that he has written.